Dr. Neeraj and colleagues for accepting my request to come to the department and share some of the work which we have done at Chemistry-UniversityofLucknow. I was more impressed with when I received that can we have linked it with something called entrepreneurship. I have 2 slides to show on this, and I have an opportunity to bring an entrepreneur with me, Professor Dr. Anil in CDRI, and he has already launched 4 products from technology transfer. So that is what you can have a live example on how chemistry can be involved in innovation and entrepreneurship. I don't know why he has not started his own company, but he has given that to the other company. But there is an opportunity for him and other colleagues like that. Right. So with that I will start. So this is what I could find when after this, a very nice book written by ACS president, ex-ACS president on chemistry entrepreneurship, and it describes what are the challenges we come across and how we should do it. And we are not only talking about this. You can see that 2020 there is this kind of conclave where the senior people, one of them, the author of this book, he talked about entrepreneurship in chemistry. So it's a very important, and the importance of this can also be looked at from this very recent news from Chemistry itself. So we have introduced a new program in PhD. The program was PhD Drive, and specialty about this program is it is for innovation and entrepreneurship only. In all science departments, not only in particular departments, all branches of education, this is there. And if you read this line, it says the question we asked, this is a statement by Vice Chancellor. The question we asked ourselves is why should all PhD programs in the country be to produce university professors? That is what mostly we have, right? When we do PhD, the next thing we think of postdoc and faculty position, right? So to overcome this, we need to have that ideation in your education, and you need a different kind of program for that, right? We cannot look for only publication oriented research thesis. We should look into the other product oriented thesis or technology oriented thesis. So that is this program. This has also been cited in Times of India newspaper, and this talks about to solve the nation's critical issues. And the specialty of this is that there will be a project which will be oriented, technology oriented or product oriented, and the students will be given a special fellowship of 60,000 rupees per month, along with 2 lakh contingency amount. And if the product is going for startup, they will be given 10 lakh or 20 lakh depending on the requirement for starting that venture. So that kind of, and this they plan to target about 100 such program in next 5-6 years. Right. So there is a need of entrepreneurship, there is a need of innovation and technology. And I think chemistry is one of the leading science in that. Yes.
So do you have an incubation center regarding the same?
Yes, we do have in all 3 campuses of Chemistry-UniversityofLucknow.
So there are mentors who can help the students with a startup.
Yes.
So you invite students from outside your university?
That I am not sure. That details is there on website, but there are incubation centers. That I know.
With respect to the field in which we are proposing,
Yes.
the chemistry.
Yes. All it is open to all because we have all science departments, and basically mostly they are interdisciplinary approaches. So this is what I thought because we are part of this entrepreneurship conclave. So there is a requirement, and we should think thinking should start from this level, because once we have done PhD postdoc, by that time we are saturated. We have only one direction set to become a faculty or to become a scientist or into some industry. But this is a time when we can think, right, and we can take a part in that time. So coming back to my work, which we we have been doing at its planning in last 5-6 years is on CH functionalization. It is also one of the new approach in organic synthesis, and that has taken a lot of advancement in last 10-15 years. And some of the reactions which we never thought of, like we always think that if we want to functionalize benzene, first brominate it and then do Suzuki reaction or Hack reaction or something. Now you don't have to brominate it. You can directly take a benzene type of scaffold and make a direct carbon-carbon bond. So that kind of approach is solving several problems. It is reducing the cost in several methods. So that is CS functionalization. There are traditional approach like functional group 1 will be converted to functional group 2 and then they can be coupled together to make a carbon-carbon bond. And in direct CS functionalization you can convert directly the CS bond into a desired functional group, and or you can have a functionalized molecule and you can couple it with another CS bond to make a CS. And third one, recent lot more interest is when you can couple two CS bond directly. Right. So in this direction, this has different approaches. Most commonly started was metallic CS bond activation, where a CS bond was converted into carbon metal intermediate by different approaches, and then you can functionalize that. Another approach is CS insertion between CS bond, where carbene and nitrene chemistry can take place, and CS bond homolysis, where the CS bond can be broken into radicals and then that radical can be functionalized. This chemistry is not new, but the application and the approaches are new now. Right. There is another term. So there is a confusion between students many times, the CS activation and CS functionalization. These two terms are like a CS activation is subset of CS functionalization. All CS functionalization are not CS activation. When the bond breaking of the CS is in rate determining step, and then there is a CS functionalization, we call it CS activation step. But if it is not, then we can call it CS functionalization but not CS activation. Okay, for example, enolization is a very fast process. So the CS bond breaking is not a rate determining step, but in the process you get the CS bond converted into CG bond, which is a functional group or some other group. So the process is CS functionalization, but it is not involving a CS activation step. So with this we got interested into some of the functionalization of heterocyclic molecules, and by looking at literature we found that melamine is a very good coupling reagent with the if you have a suitably placed directing group in aromatic compounds, and some reports were available with different transition metal for the annulation of melamine, leading to either spiro compound or alkylated spiro or alkylated spiro annulated compound. And Jagan Mohan group has given lot of has done lot of work on this. So we thought that indole is a very important molecule, and there are several bioactive compounds with the melamine fused with the indole on C3 position and so on. So can we emulate this melamide on indole? And so we tried this with rhodium, and I am sure the results should be achieve it very effectively. That indole can be annulated with the melamide to give this annulated product. If the C3 position is blocked, then you can have a spiro compound, and you can also have some C2 heteroaryl groups, and you can get a very bioactive molecule like isopropanolactamide derivative and so on. So this we did, and then we looked at substrate scope of this. Interestingly, you can have So you can have a different functional group at the C2 aryl group like methyl, trifluoroethane and halogens, and you get a good yield of those products. The better yield will be when you have electron withdrawing group here. That also talks about something about the mechanism of this reaction. And you can do the indole without this free NH here. You could also take this bioactive molecule with the pyrazolyl derivative and you could make some of the bioactive compound. You could also take this indole and we can annulate them as well with melamine. So when we block the C3 position, the annulation leads to spiral compound, and we could make few examples for that as well. To look into the mechanism of this reaction, we did some control experiment. For example, we did a radical scavenging with using tempo and BST, and there was no effect on the yield of the product. That indicates that radical mechanism is not involved in this reaction. When there was N-methyl, the reaction was not happening and we could recover this N-methyl indole in almost 92% yield. That also talks about the role of NH in the reaction. And we compared the relative reactivity of electron rich C2 aryl ring versus electron deficient C2 aryl ring, and we found that electron deficient C2 aryl ring was producing better yield. That ratio is 3:1, and kinetic isotope effect by doing a competitive kinetic isotope effect between 1A and 1P5, we found that Ks upon Kd was approximately 4. That also tells that there is a rate determining step which involves the CH bond breaking. Based on this control experiment, we proposed the mechanism of this reaction, that initially rhodium is making this Roda cycle, which was also detected by HRMS. Then that interacts with melamine, and then insertion takes place to give another Roda cycle C, which then can undergo a rollover to C3 position if it is free, to give a Roda cycle B, and that Roda cycle can lead to this annulative product, which can finally get oxidized to the desired product. If C3 position is blocked, then we can get this reductive elimination here, and you get this alkynylated product, which then can undergo atomical addition to give this pyro product, and we could detect this intermediate also in hazards. With that result, we also looked at that emitters of pyridine are also similar scaffold as to indole. So we looked at the reaction of two aryl emitters of pyridine with melamide at a very similar condition, and we did a substrate scope for this. Reaction went very well. Some of the molecules were also confirmed by single X-ray crystals. And based on the control experiment similar to the last one, we proposed the mechanism, and as that rhodium coordinates with the nitrogen of emitters of pyridine, forms the Roda cycle B. Again, coordination followed by insertion leads to the Roda cycle C. That undergoes rollover to form a Roda cycle D, which then gives reductive elimination to product. This finally gets oxidized. Right. So then we looked at this particular thing, that when we take different catalysts, then what will happen? And interestingly, when we are taking palladium, then it is forming a different annulated product with cinnamaldehydes. Then when we are taking a rhodium, that means under different catalysts, there is a differential reactivity of this scaffold. And these are some selected examples. The yield were very good, and both electron donating and withdrawing substituent work well for this. So another very interesting example is alkylation of 3-aryl fumarine by palladium catalyst. And when we took this palladium acetate K2S2O8 as oxidant, you can also alkylation can take place of this C3-aryl fumarine in very good yield, and the compounds were also characterized by single XRT for one of the molecules. And yield are very good in this case, 90% approximately for some of them. And different alkyl groups could work well for methyl ester, cyclohexyl and so on. Then we move that for halogenation. Although halogenation can also be done under similar condition when we take NBS or NCS, and you can generate a very good ortho-halogenated product. And this is very interesting that we can now bring a halogen meta to methoxy. Right? This is methoxy being ortho-directing. If we want to do electrophilic substitution, it should be on the ortho, but here due to the directing effect, it comes to the meta position with respect to this methoxy. And again, you can do several such molecules. We move this further when we take alcohols. We can do the ortho-alkoxylation. We took a trifluoroethanol as one of the alcohol derivatives. And if we take a TFA, trifluoroacetic acid, then we can introduce the hydroxy group, ortho-hydroxylation can happen. That again happens through acetoxylation followed by hydrolysis. And this was very interesting because these are chemistry derivative, and you can synthesize, but the synthesis requires 6-7 steps. We can do it in a 2-step effectively, because in one step you have to prepare the fumarine, and in second step you can introduce the hydroxy group and you can oxidize to chemistry. So we could make some of the chemistry derivative using this approach. Again, the mechanism of this reaction was proposed based on some of the controlled experiments that initially the ortho insertion of a palladium cycle happens, which then dimerizes to this, which then get oxidized to palladium-4, and that palladium-4 undergoes the reductive elimination to give the ortho-acetoxy derivative, which hydrolyzes to ortho-hydroxy compound. So another approach is which is taking a lot of interest, attention of the organic chemist is CH functionalization by radical chemistry. And radical chemistry can be done by photocatalysis or by visible light initiation, and many approaches can be there. But the concept is in generation of radical in that. It's not a new chemistry. You can see it is more than 100 years old chemistry. 1909, Loeffler reported that formation of radical, and nicotine was synthesized using this approach. So, and whenever you know that radical will happen when there is a difference between electronegativity and the bond is unstable, right? Oxygen-oxygen bond in peroxides get cleaved when you just slightly heat that, right? So because the bond and dissociation energy is very small. So most of the approaches this happen, that is what was taken earlier. So you can do that homolysis leading to biradicals, and that radical now is very reactive and it will undergo different reactions. It can take a proton from other source, it can undergo proton transfer, so it can take a proton from this CH2, so this will generate a radical air that can now react with another radical which was bromine, for example, from air, or any other radical. It gets this, and then intramolecular substitution can take place and you will get a nicotine. So, but this is 1909 chemistry, and not much after that Barton did a lot of work on this type of chemistry. But then it did not pick up too much on industrial application. And the reason was that you require UV radiation and high energy sources for that and so on. But recently there is a lot of development in visible light mediated reaction, and that makes it more efficient and doable. So a little bit from one very nice book on organic chemistry, Clayton, and this is for students. The stability of free radical, because that is leading to a design of a different reaction nowadays. And we know that carbocation are stabilized by electron donating group, carbanion are stabilized by electron withdrawing group, and interestingly radicals are stabilized by both electron donating as well as electron withdrawing group. And this book chapter they explain very nicely that how this radical, when it is in highest occupied molecular, single occupied molecular orbital of radical, when it goes, so more electron comes there, it gets more stabilized, then only one goes there. When it is a donating group, when it is a withdrawing group, there is more stability. And this understanding helps us to decide the mechanism of a reaction. Sometimes, if we are confused whether reaction is going by electrophilic substitution or radical mechanism, and if we do the same experiment taking an electron deficient species, and if reaction rate is not much affected, that gives an idea that it is not going by electrophilic substitution at least. There is a different mechanism, right? So this is one such experiment they have demonstrated that there are different substituent jet and there is a CS2 radical is being generated, and you can see that Hammett plot rho, we know that it should be a straight line if the mechanism is similar. If there is a dip in change in the slope of the line, then there is a change in the mechanism. And you can see that when high methoxy and hydrogen from 1.9 to 1, right? And then it's again start increasing and to nitro it becomes 4. So methoxy is also having a better rate than hydrogen, and nitro is also having a better rate than hydrogen. That means that there is a species which is generated in the reaction which is stabilized by both electron donating and electron withdrawing group, and that's radical. So this is from Clayton book, and this very nicely explained chapter on radical mechanism. And because of this reason, free radicals behave both as electrophile and nucleophile, and that we can see from the diagram which was there in previous slide, this one. Because here you can see there is an electron which is high and here it is a deficient, right? So they can behave both as electrophile and nucleophile, and that is again explained very nicely that when it is an electron deficient species next to it, right? So it will be react as it will donate electron, take an electron, hydride it, right? And it will not add to the alkene, right? Because it is electrophile and this alkene itself is also electrophilic, electron deficient alkene. So two electrophile will not be reactive. But when this radical is here and the alkene is electron rich, methoxy substituted alkene, then this radical will add to this alkene because this will behave as an electron rich species and so on. So they can behave as both electrophile and nucleophile. This is something which is going on recently, that you can generate a nitrogen centered radical, you can also generate a carbon centered radical, and then you can functionalize them accordingly. So you can generate a nitrogen centered radical by different ways, a different type of them. It can be nitrogen which is sp3, so you can have a little cation. It can be sp3 with a simple radical, or it can be sp2 radical. And then these can undergo different type of 1,5 hydrogen atom transfer type of reaction. So from the 5th position hydrogen can be transferred to the nitrogen radical, and then you can functionalize that fifth or sixth position, or you can even cyclize them. Right? So this type of reaction, they are continuation. Lot of work has been done in this direction. These are some examples from the literature on this. That there is a NH base coupled, proton coupled. So proton coupled electron transfer takes place in photosensitizer, and you can generate a radical. That radical now can undergo relay reaction. So this radical can add to any species. A new radical will be generated. Either you quench that place, so only one radical functionalization will take place. If you don't quench that, you can add some new species, so that new radical generated will now again go and attack that new species, and a relay reaction can take place. So there are both type of literature available in this. You can see that in this case, the first, this radical will be generated, this nitrogen radical, and that can react this there is alkene in intramolecular, that cyclizes and new radical is generated at this place. This radical now can add to an unsaturated alkene and can lead to this molecule, which can be either generally quenched, so you get a relay type of reaction. And similarly, this can be done by various photocatalysts. Now organophotocatalysts are there. They have used the iridium photocatalyst, and now many people also report without photocatalyst, just visible light, right, and so on. So again, on this direction you have a simple malonitriles. This CH can be generated radical, and then that can add to alkene, and you can elongate alkyl nitriles you can get. Right? So we also got interest into this type of chemistry, and while doing that, we found that the alcohols, trifluoroalcohols, can be generated from trifluoroalcohols. We can generate a carbon-centered radical by tempo, and that carbon-centered radical can add to heterocyclic molecule to lead to generate hydroxyalkyl derivative. And if it is a fluorinated alcohol, then you will get hydroxyfluoroalkyl compounds. And we did this with indole, and you can see that different substituted indole worked well for this reaction. And then we also did this for imidazobridines, and they could also be selectively C3 hydroxyalkyl in good yield. And various electron donating and electron withdrawing group worked well for this reaction. So the next part was how this reaction is happening. To understand that, we did some control experiment. Again, a radical scavenging experiment showed that the reaction involves radical mechanism, because the reaction got quenched. We got no product under this condition when BHT was used. But there was a side product from this BHT, which was this quinone-methyl type of derivative, which I'll talk about later. And when we have trifluoroethanol and BHT only, again there was no product. And tempo, when we took in C2, we could detect the OH tempo. So that means this tempo is abstracting hydrogen from the species. Based on this, we proposed a mechanism. We were not very sure, so we proposed 3 different pathways which are possible, because we don't have exact evidence what is happening. So either the intermediate one can form, that is C-centered radical, and this intermediate can abstract a C3 proton from the indole and can generate radicals at C3, and can do a radical coupling to give the product. Otherwise, this can add to an indole C3 position and generate a C2 radical, which can then undergo a proton elimination and generate a product 3.
which we believe this is more appropriate, but at the same time this can also undergo oxidation to this iminium ion, and that can release the proton to give the intermediate state. And we also showed the application of this. This is a zolmidine, which is a drug molecule, and easily you can functionalize at C3 position using this approach. And you can also use this for making a heterobisaryl derivative, because this is a nice intermediate for several active molecules. As I said that in control experiment we got this quinone methyl. So I asked the student to further explore that and make a method for making this quinone methyl derivatives. And we also did the tempo catalyzed. If you don't add alcohol there, and in IPA, which is secondary alcohol, we can get this quinone methyl derivatives. And there are some examples where you can see that the good elements were obtained for this. Mechanism was more or less same as previous. We could prove that it is a radical mechanism by quenching and trapping this intermediate by in radical scavenging experiment, and also finding out this protonated tempo. So we believe that first that DHT gets this radical, CS2 radical, which can add to C3 position of indole, and that leads to this alkylated product which can get oxidized further to quinone methyl. Again, this is a interesting which we have not yet published, that we could also use for alkoxidation of quinones, and different kind of alcohols work very well in this condition as well. This is a TPHP mediated aminomethylation of imidazopyridine. We were actually doing something different here. We wanted to do C3 amination here. So we took imidazopyridine and some amine, 2-aminopyridine in PhD. But we found that instead of C3 amination, we are getting CS2 NH. And then we explored this thing and it went very well. Several compounds could be made using this strategy. And again the mechanism was proposed based on that there is a generation of methylation of pyridine by the carbon source is TBHP, and that gets oxidized to iminium ion. This iminium ion then reacts with imidazopyridine in a nucleophilic way. So this C3 position is a nucleophilic in nature, that reacts to this iminium ion, generating this radical cation, and that can generate a final product. Another approach we developed for selective acylation of imidazopyridine using aryl glyoxylic acid as a acyl source, using K2H2O3 as O8 as oxidant, and again several derivatives can be prepared, and you can also functionalize zolmidine, which is a drug molecule, under this condition. And mechanism of this reaction is this: when you heat K2H2O8, it generates the radical anion. This radical anion can accelerate the decarboxylation of this, leading to acyl radicals. And this acyl radical adds to the electron deficient pyridine ring of imidazopyridine to generate the radical B. That again leads to product. And this we have proved that there is a generation of intermediate A by isolating the benzaldehyde in the reaction system, also trapping it with tempo, and also trapping it with DHT. This is very recent work which we developed, that we can have a method for doing different kind of reaction using same reagent. So it is a select flow mediated functionalization of quinoxaline norms, and You can do alkoxyl alkylation, you can do sulfonylation, amination and salination in this one. So we can do it with the natural products like menthol, you can take cholesterol and so on. So we could develop a very robust method for C3 functionalization of phenoxylate using select fluor as a reagent. So here you can do the sulfonation, and here you can do the amination, and the limitation of this was that we were only able to do amination with primary amines, we were not able to do it with secondary amines, but this we use to make this drug molecules that you can take the O-ethyl and then you can have ester here. That ester you can hydrolyze to get this compound, or you can have this molecule and then you can functionalize, make a chlorine layer and you can do substitution. And again the control experiment by in presence of BST indicate that it is a radical mechanism. We could trap this two intermediates in this case. So the mechanism was proposed that in presence of select fluor we get a radical cation which is A that reacts with either ethanol to form this radical B, and fluorine can abstract the hydrogen, can undergo the fluorine coupling, and the elimination can give you product 3AA, or from there hydrogen atom transfer can take place and we can get 3A. And the last part of my work is that how we can use a simple chemistry, which was the grinding chemistry. We all know that we have been doing it also for making some different things. But the problem with that is that you cannot make it standardized, you don't have a equal force, you don't have a measurable quantities of energy, what is transferred. So for that you can have a machine called ball milling, and that is one which we are using. So we can use a mechanochemical energy here for transferring to the chemical reaction, and the machine which is being used is called ball mill, and these are of two types, vibrating ball mill or planetary ball mill, which we are using this planetary ball mill mostly. And the advantage of this, you can generate a selectivity in several reactions, and I'll show the example of that selectivity. So we recently developed a method for hydroxyalkylation using aldehyde as a compound, and you can see that mostly if you do this reaction, when you take a indole or this type of nucleophilic aromatic compound, you will get a bis-indolyle. This derivative will be major product. Because under that condition in solution this gets cleaved and you get a cationic species here, and that reacts again with another molecule. So we developed some, we looked at some Lewis acid catalyst and found that zinc triplet was good one under at sodium acetate, and we get 92% of this 3AA. And when we can also optimize this by changing the number of balls or frequency and so on. We could show the generality of this reaction for several imidazopyridines substituted at aryl ring and on the side ring, and also taking different aldehydic salts, and also some other heterocyclic compounds like this also gives you simple hydroxymethylation, and the yields are very good in that case. These are again active intermediate in several molecules. This was extended to indole, and it worked well with substituted and unsubstituted indole as well as unsubstituted indole. And we can now use this type of molecule to make various compound, like you can put other aromatic compound here by Lewis, doing simple Lewis acid catalyzed substitution reaction. You can get a bis-indolyle or bis-heteroindolyle derivative and so on. And we could show the regioselectivity of this reaction, that if you protect the C3 position, there is no reaction. So only it is selective to nucleophilic C3 position. Radical scavenging experiment showed that reaction has no impact on the yield, so it is not radical mechanism. Competitive experiment with the withdrawing and donating group shows that it is better for withdrawing group 4:1. No, with electron donating group 4:1 indicates that it follows a very similar electrophilic substitution mechanism like Friedel-Crafts acylation type. And intramolecular kinetic isotope effect was not significant. That also indicates that it is not a CS functional activation that is not involved. So it is a Friedel-Crafts alkylation type reaction. And same we extended to alkylation of this by ball milling. We could take internal alkynes and regioselectively we can do the auto-alkylation using ruthenium as a catalyst. Several optimization experiments were performed and we found the optimized reaction condition. The ruthenium catalyst in 5 mole% in HESPF6, carbonic acid as additive, under ball milling gives reasonably good yield for various bisalkylated compound, trialkylated compound. Interestingly, when you have aliphatic alkynes, we were getting monoalkylation. We don't know the reason for that right now. And again, other agrocycles also we could do into two aryl alkyne indalols and so on. The reaction went very well for this as well. Again, control experiment indicates that this reaction follows a very similar mechanism as for solution chemistry, and we could also show that there is this intermediate where rhodocycle this is formed. We could isolate that, and using this we did a reaction and reaction went well. So that proves that this is the intermediate in this reaction. Kinetic and isotope effect also shows that the Ki is 2.2. There is an involvement of CS bond functionalization or CS activation, and the experiment was done by parallel lines of thing. And intramolecular competition experiment also indicates that the Ki is 2. So there is an involvement of CS bond functionalization. So based on this is a mechanism that, as I showed earlier for rhodium, there is a rhodocycle which is generated here that coordinates with alkyne, forms this intermediate, which then releases this, and again you get this rhodocycle which again interacts with another alkyne, so you get a double alkyne alkylation in this case. So these are some other reactions which we have performed in our group. We also work on some kind of mixer catalyst, and we also develop some other simple palladium catalyzed reactions, coupling reaction where you have a tandem condensation followed by alkylation and so on. With this, I would summarize that we can take a simple reaction condition and develop several methods for functionalization of heterocyclic molecules. I have shown you some example for transition metal catalyzed CS bond functionalization as well as activation in reaction, some radical mediated CS bond functionalization, and we explained some of mechanochemical reaction under bond milling. And using this, we have developed these some of the novel scaffold of heterocyclic molecules. With this, I would like to thank my group members. The work which I have shown you was mostly done by these three. Dr. Prof. Patel, he was at PDF with me, he was from CDRI Lucknow. And Vicky Sinde is in Jammu now in US. And Dr. Sonam is going to Ohio State University now, just completed PhD. So the work which I showed you was mostly this. The other students are currently working with me are also working on similar areas. My collaborators, Professor Brenton DeVos from University of Rhode Island, USA, Professor K. Kawasparan, my postdoctoral mentor as well as my collaborator. Professor Mukund Jha from Nitpising University, Canada. Professor Dalip Kumar at BITS Pilani is a very senior professor and my mentor as well. And Professor Venu Das from ISCS. We worked on some of the medicinal chemistry work on treatment. Not the least, I would like to thank the funding. I am very fortunate to have funding from SERB, DST and CSIR, UGC and BITS Pilani of course for all infrastructure and resources. Thank you very much for your kind attention. This is the campus of BITS Pilani. It's a